All right, good morning. Today we have the, is it working? Yes. Today we have the second session of this course on economic and sustainability aspects. To give you, to remember where we are in the course. So the introduction session, we started with looking at least climate conscious design, showing that it's different depending on the context we are building in. Today we're going a bit deeper in what is thermal comfort actually and how can we analyze a climatic context to link both of them. So that's the aim of today. We're mainly focusing on average climate data, so monthly data, while next week we will go in more detail in very precise weather data, hourly data. So that's the difference between this week and next week. So today we're looking at climate, but in a very generic way, monthly data linked to what is thermal comfort. So very briefly, I will wrap up what we saw last session on climate conscious design, and then we go to the climate analysis and the thermal comfort analysis. At the end of the day, I will also briefly introduce the first assignment of the paper you are writing for this course, which will be where you can start working on in the coming week then. So climate conscious design, what did we see last week? Well, why are we first of all focusing on that part in this course? Because it's a first important strategy if we want to reduce the environmental impact of our buildings, mainly the operational phase of the buildings. So climate conscious design is a strategy to reduce the energy use of our buildings. And to do that, to enable climate-conscious design, we first of all need to understand the climatic context we are building in. We need to understand what comfort requirements are, and we need to understand what design principles we can use to respond to this climatic context in a good way. So these are the essential elements. So last week we just looked, or what we mainly did is look at how different architects or cultures respond to the specific context they are building in, to learn to take home messages kind of for the next sessions in this course. So what we want to avoid is an excessive energy use during the operation of the building, either for cooling or for heating. And that we do by looking at the climatic context we are living in. We saw that the climate is very different depending on where you are on this planet. And we categorized it in very different climatic regions, let's say, where we saw that people built differently depending on the region. So we started first with looking at very cold climate. So if you look at the left side of this slide, we see that there it's even impossible. So at the really north part of our planet, it's impossible to live in a comfortable way without heating. But still, people try to survive there by having very small buildings, very compact buildings, so that the envelope of the building is very small compared to the heated volume. It's a dome, and then people use local materials because there's nothing else available. So in this case, it was the ice blocks together with the skins of animals. Also in the mountains, we see that these local materials are the only mean to build. So wood is typically used, timber is used, and natural stone. And there people really look at the orientation they have to build in. So looking at the wind directions, for example, to be sure that, for example, for the storage of grain, that it can dry throughout the seasons. It's covered to be sure that there is no rain in there. It's tilted up to ensure that the snow cannot reach it in winter time, but also that ventilation is beneath the building possible over the year, or when it's not snowing. And so the area that's really used actually is very small compared to the full building. So all the other parts are actually protection again for this small sized room. Then we looked at the warmer climates and saw two different things. So first of all, when we are in a zone where it's hot but dry, so not too humid, so this you see it's already more humid. When it's cold, warm and dry, what we typically do is protect ourselves against the sun to avoid overheating, and use also the street patterns to ensure that we have shadow in our buildings. We typically have smaller windows But of course we need daylight inside, so balancing between a sufficient daylight but avoiding overheating is there an important strategy. While if we look at the climatic zones where we have high temperatures in summertime but more rain or wetter climates, in these humid climates we will not only protect ourselves against the sun, but we will also use ventilation, cross ventilation we call it, so we will use the wind velocity to ensure that we feel comfortable inside. So that's the way of protecting. So typically you see architecture with openings, but still covering, protecting against the sun. If it's the same here at this side, so very hot over the year, and then a lot of humidity, we see the same. So I have protected overhangs to protect ourselves indoors. We have balconies with openings, we have inner doors with openings so that we can ventilate a lot, but typically shut everything when it's needed to protect against the sun. So outside shutters, but with openings for allowing for the ventilation to take place. The other extreme on the right-hand side of the slide is again the warm climate, so the temperatures is more or less the same, but the difference is that here we don't have any humidity. So their ventilation is not that important. So what we typically see there is a very massive building, so very heavy building materials used, or people use the earth to dig in their homes. Small windows, so a lot of protection against the sun. We keep the sun out, and we have thermal mass to ensure that the temperature inside is lower than outside. And that is based on what we call a time lag that we try to reach by this thermal mass. So the more thermal mass you have, the larger becomes the time lag between the peak outdoor, the peak temperature outdoor. So this dark line is the outdoor temperature. And here the dotted line is the indoor temperature in a building with a high thermal mass, so heavy buildings. So what we see, so if this building is not used and one measures the indoor temperature, we see that the peak of the temperature inside is later than the peak outside. And this has to do with this thermal mass. So if you have a lot of mass, there is a delay in the peak. And also we see a reduction. So the highest temperature here is much higher outdoor than indoors. So this has to do with this thermal mass. That's the effect of using thermal mass in a hot climate. So you delay the peak and you reduce the peak. So typically when we have the peak here at noontime, here we have the peak at 6, 7 o'clock in the evening, meaning that when you come home, typically you have still a comfortable indoor climate, when it's of course not too hot. But typically when this would be too cold, here we have sufficient heat stored. The more mass you have, the more stable it becomes a temperature. So the peaks which you see outdoors, this difference in temperature is much higher than the difference in temperature here. If you have a light building, then this variation in temperature outdoors, you will see the same happening indoors. While if you have a lot of thermal mass, the temperature becomes more stable. So the peaks are the variation in temperature is reduced. So it does mean if it's not well protected and you let the sun in, and the temperature heats up, it's hard to get the temperature down again. So we have to be careful that we keep the sun out when we have these high thermal mass buildings. While if you have a very light building, it's easier to get the temperature down again, because if you ventilate a lot, the air temperature goes down quickly, while the temperature of the materials don't cool down that quickly. So that's why this thermal mass results in a more stable indoor temperature, but be careful then that it cannot raise. So based on these different climatic contexts and way of building, we could see the different measures can be taken. So first of all, this thermal capacity, which I just explained, is important. Shading is important, especially to overcome overheating. But sometimes in colder climates, we don't want to, especially when there's a big difference between winter and summertime or cold and warm season. We only want to keep the sun out in summer and not in winter, because we want to use these heat gains to reduce the heating. So what's then important, that you have a an adaptable shading so that you can change the shading in summertime and in wintertime, or in sunny days and not sunny days. Airflow is important, especially when we have humid climates. So then we use it to cool down, to take away the moisture and improve the thermal comfort. And that we will see later on today, because we will see that thermal comfort depends on the temperature on the one hand, but also on the humidity on the other hand. So when it's too humid, even if the temperature is the same, we feel uncomfortable. So that's why this ventilation is important in humid climates. And to increase the airflow even, we also saw architecture last time with wind catchers to increase the wind speed. So really capture the wind and make sure that it enters our building. We can also humidify when it's too dry, or the opposite, we can dehumidify when it's too humid, but that's not, so if you want to do it in a passive way, that's ventilation is the most important. If you want to increase the humidity, we can typically work with water pumps outside, or make sure that we have water there and that it's evaporated, and then the air becomes more humid. And then finally, we saw also strategies at the higher scale level, so that city scale, street layouts, street canyons, or the sections with height are also measures that we can take to improve the climate indoors. So this was learnings from traditional architecture. I just want to end this part or conclude this part with an example of contemporary architecture who use these principles to make sure that they have a building with a low energy demand or low energy use. I'm not sure if anybody knows the building. It's an office building of Baumschlager and Eberle in Austria. So it's new build. And what they wanted to do, they want to create a building with no active heating nor active cooling. So it's building that's completely passive. So there are no heating system inside, there is no cooling system inside. And so one really wanted to use these strategies that I've shown before. The learnings from that they wanted to use here to make such building possible. So how does the building look like? It's a building with a square footprint, so meaning it's quite a compact building. So it means that the envelope is not that large compared to the volume that one wants to. So it's not a cube, but it's a very compact building. It has 6 floors in total, mainly office buildings. But there is also a kitchen on the ground floor, and the top floors are for exhibitions. And typically one thinks that maybe in future it could also reside residential functions, but for now that's not the case. So it's in Austria, suburban area. That's important to know. So it's not in a city center, it's really at the suburban side. So there's a lot of wind access, but also solar access there. So there are no surrounding buildings influencing the behavior of the building today. As you can see here, the walls are quite thick, which you can also see on the plans. So they make use of this thermal mass to have a stable climate indoors. So that's what their strategy was. And as you can see, there are many windows at all orientations in order to allow for ventilation, cross ventilation in many different directions depending on the wind orientation, but also to ensure that every room can be cross-ventilated, but I'll come back to that. What you can also see, but I show it on the previous slide, is that the windows are, they have, the windows are, it's not fully glazed, but the windows are always designed from floor to ceiling. So they have very high windows. And the reason is that they want to have daylight, sufficient daylight, deep into the building. So the higher you make your window, the further the daylight can reach. So even if you have the same glazed area, but the windows are lower, then the daylight does not penetrate that deep into the building. So that's why they opted for very high windows to reduce the need for artificial lighting. So the heat demand is not 0, it's 8 watts per square meter, but it's so low that it's captured or it's fulfilled by the artificial lighting actually, because if you have artificial lighting, it also radiates heat, and that they actually use for this very small demand of heating demand. the electricity use, there is electricity use for steering things, so the control system, I'll come back to that, which needs to be covered, of course, by renewable energy then to keep it as a zero energy building. Total floor area is 2,700 square meters divided over these 6 floors. So what was their aim? Their aim was, so if you, this is the outdoor temperature that you see in blue. And so that's the external temperature. And this is the green line is the internal temperature of an empty building. So if you just would put that building there and it's not used, it's not controlled, that would be the measurement of the indoor temperature. Now what their aim was that so the gray bar that you see here indicate, it's not very visible on the slide, but here's the gray bar, that's the comfort zone. So between 20 and 26 degrees, more or less. That's the comfort zone. And so what they wanted to achieve is that when this building is used and controlled well, the temperature should always be between the 22 actually and 26 degrees. So the building is called BE 2226, and the name comes from 22 minimum temperature and 26 maximum temperature. So, and BE stands for Boomschlager and Eberle. So it's the first letters of their two names. So BE 2226 is the name of the building. It's here on top of the slide. So the BE is Boomschlager and Eberle. 22 is the lower temperature, and 26 is the upper comfort temperature. So their aim was to have a building where the temperature is always in that comfort zone without active heating or cooling. So first of all, there's a difference. If you don't use the building, they don't reach that. So you see that the temperature is even below the comfort zone. When people are in the building, we see that that temperature goes up. Why? Because people radiate heat as well. We all radiate heat. If this room, if nobody is here and you measure the temperature, or you have 20 people in here and you measure the temperature, there will be a difference because people radiate heat. But also you use computers, there are printers, there are a lot of appliances which also radiate heat. And that makes this difference. So if you don't have this occupancy, the temperature is lower inside than when you have it. And the better your building is insulated, the higher this difference will become, because you capture the heat and you keep it inside. While if you would have the same building without insulation, all the heat that is produced in the building goes outside again through transmission losses. So that's why a good insulation layer is important to ensure that the heat that is produced inside is captured in the building. We still see that sometimes it's below and sometimes it's above the comfort zone. So they did introduce a control system for opening panels, not windows, but panels, so that air can come in and go out, let's say, but also lighting systems to make sure that people have sufficient light. Sometimes they put the lights on even if it's not needed, just to be sure that it's not too cold in a few days in a year. So the lighting is actually a backup system to make sure that when it's a few days a year too cold, they can use that instead. But so they managed to reach this. So they measured it for a few years and they saw that normally they always can reach their goal, except for a few weeks over summer or days over summer, depending on the year. When the nights don't cool down sufficiently, it's getting too hot in the building. So when you cannot ventilate at night, when the temperature cools down, then they saw it's impossible to stay within this comfort zone. And then it also became too hot in the building. So it's really important, their concept only works when there is sufficient difference between day and night temperature. When you have hot summers where the night temperature doesn't cool down, their principle doesn't work well. So what did they do? So first of all, they made a very well insulated building. So to keep all the heat that is produced inside, to keep it inside so that it's not lost. And also very airtight, meaning that there are no losses through air that leaks out of the building. They have a high thermal capacity for the summers. So the very well insulation is mainly important for the winter time, But the high thermal mass is important for the summertime, to have this stable indoor temperature and not a high fluctuating temperature inside. And they very much invested in controlling the natural ventilation. So they don't have an active ventilation, so there's not a mechanical system to ventilate. It's with opening windows, and there's kind of a chimney with an opening in the roof to get the air out. So it's a natural ventilation, but still they need to control it to make sure that it's not ventilated too much or too little, because the drawback of having a very well insulated and very airtight building is that your indoor air might become unhealthy because the quality goes down if a lot of people are inside. So ventilation is crucial to have a healthy building once it's very airtight and well insulated. And typically we do that with mechanical ventilation. So we typically have fans that first gets the outside air into the building and extracts the used air, let's say. But then you have a lot of heat loss, and you need energy for this, for mechanically steering the flows. So they didn't want to do that. They wanted to have natural ventilation, meaning that they still have loss of heat when they ventilate, but they reduce the ventilation rate to a minimum in wintertime, and they increase it in summertime. So they really try to control it as much as possible, considering the users. But I come back to that, how they exactly did it. So there is no active heating nor cooling, but they do use the light system for very cold days, even if no people would be inside, or they arrive at 8 o'clock. They already put the lights on at 7 o'clock when the temperature is too low to start heating up the building a bit. So that's kind of their backup system, which we could question if that's the best way forward, because it's not really an efficient heating system, of course. Now, what's the daylight design? They want to have sufficient glazing to avoid too much artificial light, the need for too much artificial light. So they did a lot of simulations, and for that building, the best number was 16% glazed area of the facade. So 16% of the facade is glazed. And they want to have a good distribution of the daylight, so that's why they have these high windows, to make sure that the light penetrates deep into the building. So that's the reason for the high, small windows. And the artificial lighting in the mornings when it's dark anyway, they use that as backup system for the heating system. So how do they control then the indoor air quality and make sure that it's not ventilated too little or too much? Too little because of a healthy indoor climate, but too much because of heat losses then. So what they did is, if I go back, probably you can see it better to the facade. Here you see the windows, and next to each window you see a wooden panel. The wooden panel can open and close. The window not. The window is fixed. But the wooden panel can open and close, and that's their ventilation rate. So here typically we open windows. They didn't want to do that because it's much cheaper and much airtight. The windows are better airtight when it's a fixed window and you don't open it. So that's why they opted for having this panel instead of this window opening. And the windows, they steer it. So the opening, the panel can fall at inside actually with chains to allow for this ventilation. And what they do, so if I go further, it's rotating, sorry. I thought it was falling, but it's rotating. It's another building that it's, so it's rotating, open, so it can open and close. And the opening and the closing of the panels is steered. So people who are sitting there can decide to open a panel themselves. So they can click on a button and then the panels open. But constantly, there's a measurement of temperature, CO2 concentration. So the indoor temperature is measured all the time. The concentration of CO2 is measured all the time. The outdoor temperature is measured, and the relative humidity inside is measured. And so when people don't open it, but the CO2 level is too high inside, or the humidity is too high, or the temperature is too high compared to the outdoor temperature, the panels open automatically. If people say, I feel too cold now because it's opening, they can manually close it again. But the system can overrule it after a while if again, the indoor temperature is not under control anymore. So it's a dual system. So people can still decide themselves if they want to open yes or no, but the control system can overrule if it has a bad influence on the thermal conditions or the quality of the air inside. Why did they do that? Because it seems that people sometimes feel more comfortable under the same conditions when they have control or not. So it's also a perception. If you are in a room and you cannot open anything, even if it's comfortable objectively inside, you can feel uncomfortable because you cannot control anything. So that's why they decided to not rely fully on a control system based on objective measurements, but they also wanted the people to have some influence at least. So the ventilation opens automatically, the panels open automatically when the CO2 concentration is higher than 1,200 parts per million, and that's the level of an indoor air quality. So when it's higher, then it's not good for human beings, for concentration, for example. Or when the temperature is too high compared to the outdoor temperature. So that's why you need to measure both, because if the indoor temperature is too high, but outside it's even higher, it doesn't make sense to open the panels. So it's really the two parameters together that define if or determine if the panels should be opened, yes or not. Yes or no. And then secondly, an important thing is the ventilation. So it was decided to use as the amount of inner walls is as low as possible to allow for ventilation, because the more walls you put, the more difficult it becomes to have a good ventilation in the rooms, because you block the airflows. So that's why they tried to define in a good way where the walls should come and where it should be kept open. Which sometimes works well and sometimes not. I'll come back to that. But so what they try to do is put the windows in all orientations. So you could argue, so why do they have the same windows openings in all orientations? Because normally you should have a lower amount in the area in the north and a higher maybe in the west or whatever, depending on where you are. Well, here they didn't do that. You can just turn the building and it would remain the same because of this ventilation. So they did an investigation and they found that in that location, this was the best choice. Now, what does work well is it is well ventilated, but they have some issues with acoustics because now everything is open. So if many people are working there, they have some issues. If the amount of people are limited, it's okay. So what you see when you visit the building is that people, and what's also an issue is the light is okay, but sometimes it's overlit when the sun is shining and people are working on screens because there's no solar shading foreseen. So then you see that people indoors use curtains already to protect themselves against the sun, to be able to read the screens actually. So there are still some things to be improved, but overall it functions really well. They did use some special measures. Oh, if I go back, if you look at the wall build-ups, so they're bricks, and you could say, oh, there is no insulation, but there is insulation. So what they did, they have a special brick with holes inside, and they put insulating materials, but just balls inside the bricks. So it's one layer, which is a structure and the insulation, and they can take it out again afterwards. The outside is plastered, and the inside, they don't use a gypsum plaster, which we typically do, but they use a lime mortar, lime plaster, which is better for regulating humidity. So it can uptake humidity and it can release it again when it's so it's a regulating layer kind of for humidity inside. And when you ever have the chance to visit the building, it's really worthwhile because you feel it inside, that it's a different finishing layer. It really has a different effect. You see also, maybe that's also important, there is no solar shading, so there's no active solar shading or something that changed, but what you do see is that the windows are put at the inside of the wall. So actually the thickness of the wall, which is 70 centimeters in this case, so it's a 70 centimeter thick wall, is actually a kind of shading already, because on top you have the 70 centimeters and at the two sides. So in that sense, there is kind of a shading, but just a fixed one. And it only works when the sun is very high, of course. So in summertime, when the sun is at a high position, it protects the windows against the sun because of this 70 centimeter deep eaves. When the sun is low, it doesn't protect it, because then the sun just enters the building. You have a question? Could be. So a cavity wall is different, because then you have, but the cavity wall has some drawbacks. So when you have an inner wall, then you have your insulation, and then you have your outer finishing layer. Typically, the thermal mass is restricted to the inner layer, because once you have an insulation layer, you block the use of the thermal mass. And that they didn't want to have here. So they really wanted to use the 70 centimeter thick mass for the thermal regulation inside. So with the cavity, that doesn't work, because then you only have 14 centimeters of thermal mass. Now they have the 70. And that's the reason here why they decided not to go for a cavity wall. Yeah. But we checked with simulations this building, and then we saw that from this 70 centimeter, actually only the inner layer of 20 centimeter or 15 even is used. So it's an over-dimensioning of the thermal capacity, according to simulations. And we discussed it with the architects, but they say that simulations cannot capture everything. And they believe that still the 70 centimeters would work better than if we would have built the same building with a cavity wall or a smaller thermal mass. So the dynamic energy simulations rely on algorithms that try to capture the full behavior of flows. But it seems that they argue that it cannot capture the full behavior of the building, and so they believe it's still better what they do. Yeah. Okay. Okay. Yeah. So here the moisture or the plaster is not used to regulate the moisture from inside to outside. It's only to regulate the moisture that people create by respiration. So what it does is it captures the moisture, so it's actually cut or captured in the lime, and then it dries out again. When it's at night, for example, when nobody is there and the temperature is still high, it can dry out. So it's just a regulation inside. It's not something that regulates inside, outside. So it's only for the humidity that's created inside, let's say. So it's only regulating between the material and the indoor air, nothing across inside, outside. That's through the ventilation then. Yeah. All right. So I just wanted to introduce this building to show that also in temporary building, we can use these learnings from traditional buildings, from climate conscious design to try to create modern buildings, let's say, with a good thermal comfort inside without active heating and cooling. Maybe something more, I'm just thinking about it when I see the picture. Something important that they did as well is having high ceilings. So the floors are high. It's not the regular 2.20 meters that we typically have here, or 2.50 meters, but it's about 3 meters high. And that really helps, because that's the only way how they can keep the CO2 concentration low enough to not to over-ventilate, to have a healthy indoor climate. So the over-dimensioning of the floors actually is a very important mean to ensure that the indoor air quality is sufficiently well. And I must say, when we visited the building there, it's still under-occupied. So the number of people that work there are lower than the maximum it's designed for. So I'm still wondering if it would work as good as it is now when it would be fully occupied. I'm not sure if that would still be the case then. So that's something to keep in mind, that the measurements they do, it works well, but it's with in a situation where it's underused actually. So the number of people are less than it's designed for. But a very nice building, I think, to see what we can do. At least if it would be not zero energy, at least we could reduce it to an important extent. All right. Let's go and have a look at what thermal comfort is, or how we exchange heat with our environment, to see what we can do then to have a good thermal comfort inside. So first of all, it's important to understand how we exchange heat with the outside air to feel comfortable, to make sure that we're in balance and feeling well. So there are different ways. So first of all, what we do is we radiate. So two objects at a different temperature radiate to each other, and it's always from the highest temperature to the lowest. So when you are in an environment where everything has a lower temperature than you have, you actually you give heat to the environment. While if you're sitting next to a radiator, a heat radiator, you get heat from that radiator because it's a higher temperature. So that's also how we exchange heat with the sun. The sun is an object at a very high temperature, providing heat to us. So when you sit in the sun or in the shade, you feel different, not only because the temperature is different, but mainly because the radiation is different. So that's the first one. So we have radiation. Then we also have, when you touch something or when you are in contact with something, there is a heat exchange from you to the other object, and always going from the hottest to the coldest. It's not radiation, but it's actually through conduction. So you really, there's just a flow of energy. And so the higher you insulate yourself, the more clothing you wear, the less heat you can release through conduction. So it's actually a protection layer. So that's why we have thicker clothes in winter or when it's cold, and less clothes or thinner clothes in summertime. We evaporate also through when we sweat. So when you go running, you start sweating. That's because your body is getting too hot and wants to exchange or get rid of the heat in a quick way. And that's where we have this mechanism of sweating. When we, so the respiration, of course, is also a way of releasing heat. And then we have convection. So when there's an airflow going along your body, it takes the heat with it. So that's why sometimes we have fans just creating a wind flow that helps this heat release of bodies because of the convection. So we have conduction, convection, radiation, and then two more mechanisms here. It's the sweating through evaporation then, and the respiration. The energy that's coming from the sun is just a mechanism of radiation, but it's an object at a very high temperature, so radiating a lot of heat, which is sometimes also reflected. So if you would have here a dark surface, or you would have snow, for example, the reflected radiation is different. So when you are sitting next to snow, you can even get more radiation because of this reflection of the sun. So these are the mechanisms. So it means we have radiation, warm object radiating to a colder one. We have conduction, and there should be really contact. So if this is a hot one and we hold it, we can burn ourselves in this case, but that's the principle of conduction. And then we have the convection, it's the airflow actually. So these are the three mechanisms of exchanging heat with our environment. And then just looking at the sun, although it's not the only way of exchanging heat, it's an important one because it influences the weather conditions where we are in. So I come back to thermal comfort later on, but I will first introduce more the weather or the climatic, the weather data or parameters that define our comfort. So first of all, what's happening? Well, the sun is an object at a very high temperature, and it's releasing more or less 342 watts per square meter. So that's the amount of energy coming from the sun. It's not always reaching us. How much reaches us depends on where we are on the planet, so the distance to the sun, but also the clouds formation, so how much clouds we have and what's kept in the atmosphere and what reaches the Earth. So it really depends day by day and location by location, but in general, part of this amount of incoming energy is not reaching us because it's reflected back by this layer of clouds, also dust that is in the air or small particles that in the air blocks or reflects this solar energy. Part of it is also absorbed higher up. So in this atmosphere, part of the energy is absorbed, and the absorbed energy is released either back into the atmosphere or partially reaching the Earth afterwards. Of the part, so the part that does reach the Earth, again, we have different things happening. Parts are reflected back, especially if we have light parts or water ponds, which are reflecting to a high extent. A high amount of this solar energy is reflected back. But part of it is also absorbed by the Earth. And then we see again different things happening, either just radiating. So when the Earth warms up because the sun shines on it, the temperature rises, and the higher the temperature, the more it radiates back into the air. Part of it will be blocked and cannot go out, is captured back because of the atmosphere. Part can go through, and then even is radiated back here because of the absorption in the atmosphere. It can be radiated back as well. Then we have also evapotranspiration. So if you have water ponds or whatever, it's heating up, and it is so the water becomes asks energy, requires energy to go from a fluid to a gas form. So there again, we use energy. And that can have a cooling effect. So that's why we typically see that when we have water ponds or we have trees that capture heat and release it back as a gas, we see it's a cooling effect. So that means it's quite a complex system of what's happening, and this also explains why we have this climate change effect, because what we see is today there's an imbalance between the incoming energy and what we can release back. And that has to do with all the CO2, but all greenhouse gases actually that are in the atmosphere today. Because we have too many greenhouse gases here, what happens is that the energy can come through, because the wavelength of the solar energy is as such that it can penetrate through the atmosphere because of the high temperature of the sun. This is a very short wavelength and can penetrate through the atmosphere. But all the greenhouse gases and other small particles here block the long wave radiation. So because everything is heating up, it's radiating back, but with a longer wavelength because the temperature is lower than the sun. And then it cannot penetrate again through the atmosphere. So it means we block here the energy on Earth. So meaning that we receive more energy than that we radiate back into the Earth, into the atmosphere, meaning that we're heating up our planet. That's actually what's happening with climate change. That's a bit a side note, but it means that there are a lot of parameters influencing the weather conditions or the climate on the Earth, because you can see that the more clouds you have, for example, that will influence the balance, but also water or not, or the reflection of parts of the Earth will also influence this whole mechanism. So if we talk about climate, we typically describe it with different characteristics or parameters. So an important one is temperature, because that will influence how we feel, humidity and precipitation, wind, solar radiation, cloud cover, and then you have other phenomena like sandstorms or thunders or snow or whatever are also characteristics. Typically, we have different indicators describing these and different units, expressed in different units. So for example, for temperature, we typically use a mean temperature, or can be an average temperature or extreme temperature. So you have different parameters. And we will look at some of them in the coming hour, but also next week. Humidity typically is expressed in vapor pressure or in relative humidity, and that's an important one. So we will typically express it in relative humidity. But let me explain what it means. So if you have the absolute humidity is the first parameter to describe humidity. It's actually describing how much water vapor is in the air. That's humidity. That's the absolute amount of humidity. And it has nothing to do with temperature. It's just how much humidity is in the air. Now, temperature comes into play when we talk about relative humidity. Why? Relative humidity changes with temperature, even if you have the same absolute amount of humidity. Why? Well, the maximum amount of humidity that can be carried in the air depends on the temperature. So the higher the temperature, the more absolute humidity, the more absolute humidity can be held in the air. So it means that if you have a temperature of 30 degrees, for example, 30 degrees Celsius, then we know that this air can hold 30 grams of vapor per cubic meter. While if we have air at 0 degrees, it can only hold 5 grams of vapor per cubic meter. And if you would have 6, well, then the vapor will become water. So it will condense. So we have condensation at that moment. So the vapor cannot go above what's maximum possible. So it will turn into a fluid at that moment. So it means, if we talk about relative humidity, we compare to the maximum amount that's possible. So relative humidity can never be more than 100%, and that would mean that we are at the maximum. So it would mean a relative humidity of 100% if we have a temperature of 0 degrees would correspond to 5 grams of absolute humidity. So it measures how much vapor is in the air compared to the maximum possible, and that depends on the temperature. So it also means if we have a certain amount of absolute humidity, imagine you have 25 grams of vapor here. If the temperature is 30 degrees, then we will have a relative humidity which is below 100%, and it's nearly, let's say, 90%. So it's actually the 25 divided by the 30. Now, if the temperature drops, if we don't have 30 degrees, but we have only 20 degrees, then it means if the absolute humidity remains the same, the relative humidity will go up, because compared to the maximum what's possibly held in the air, it's the real compared to the maximum is getting higher. So, yeah, there is chalk here. So this is the conclusion, that warm air can hold more moisture than cold air, and so meaning if the absolute humidity remains the same, the relative humidity goes down. Yeah? So the relative humidity depends on your moisture that is actually there compared to the maximum amount of moisture. So if your maximum amount goes up, the relative humidity goes down. So if this is fixed, if the absolute amount does not change, so if it remains stable, but the maximum that you can hold raises, and that happens when the temperature goes up. If the temperature goes up, your maximum amount can be higher. So if your temperature raises, your maximum amount can go up, and it means your relative humidity goes down. So what does it mean if you have an absolute amount of humidity during the day that is stable, but in the morning it's cold? So your maximum will go down and your relative humidity will be higher. While in the afternoon, when it's warmer, your maximum amount will go up because your temperature raises and your relative humidity will go down. So it typically means that these are opposites. If the temperature goes up, the relative humidity typically goes down on the condition that the absolute humidity remains the same, of course. So when we will gather data on your specific situation, climatic context, you will need to find data on temperature and relative humidity, both mornings, daytime, and evenings. Typically, be careful when you combine these. If you have higher temperatures, it should be combined with lower relative humidities, typically. So that's a trend that you should keep in mind. So relative humidity goes down when temperature goes up. So they have an opposite direction because the absolute humidity remains the same, but when the temperature is higher, it can hold more absolute humidity. And then we have the others, but I will come back to that. So for precipitation, it's typically in millimeters. Raining days can also be a number of days that it's raining in a certain context. Wind, we have different things that are important. The speed is important, but also the direction of the wind is important. And the frequency when there is not a lot of wind. So typically when it's very wind still, we also check typically where then the direction is coming from. And then the solar radiation can be in numbers of sunshine hours per day, for example, but can also be in energy really, so kilowatt hours, daily radiation, or even hourly radiation. So how many watts do we receive in each hour? And we typically differentiate between diffuse and direct. So direct radiation is just if you draw an arrow from the sun to you, that's a direct radiation. But typically that radiation is scattered in the atmosphere and indirectly reaches us. So it's scattered radiation through these clouds that are in the atmosphere. So the more cloudy it is, the less direct radiation you have and the more diffuse radiation you have. So if you have information about the direct and diffuse radiation, you can learn if it's a cloudy environment or if it's typically blue sky in that environment. And sometimes you find data about cloud cover, but that's really rare. So not many locations really measure cloud cover, so they typically give information about direct and diffuse because it's easier to measure, but then you can, from that, learn what it means regarding the cloud cover. So it's related. And then you can also have days of sandstorms or fog, frost, and so on. Now, as said, the temperature, different data are available typically, and they give you different information. So let me show that based on a graph. These are the hourly in dark blue, the hourly temperatures measured at a certain location over a full year. So we have 1 year. For each hour, we have a measurement of the temperature. That's the most complete picture you can have of temperature. Typically, that's the highest level of granularity of measuring the temperature at a certain location. But what's mostly given is a monthly average. So typically, if you look at a website with weather data of a certain climatic context, you will find monthly average data. So which means that you actually get data on this green line. So you will have 12 numbers, one for each month. So the monthly temperature in January, for example, would here be 21 degrees. While actually you see in January, there are days where the temperature are nearly 30 degrees and nights where the temperature are 10 degrees. So it means that 20 degrees don't tell you so much. You just know more or less the range, but you don't know if it's nights or there's a big difference between day and night. You don't know if there are big swings between the days in that month. You don't know that much. You only know the average temperature. Because what we show here as well, just to give you an indication, is that besides the monthly mean, we also calculated based on this hourly data, the monthly minimum and the monthly maximum. And that gives already more information because then you can see on average, there is a swing between day and night. Typically on average at night it's 17 degrees and during the day 26. So then you can already better understand in which context you are building or working because you see that there is this swing. It could be in another context that you have the same mean temperature, but for example, during the night it's 18 and during the day it's 22. That's a completely different situation to use night cooling or not, for example. And here you have also in yellow the daily averages, where you can say that even in the month of January, you have average days where it's 22 and other days where it's 15. So there is still a swing day by day. So to have the best information, you need these hourly data or daily data with swings that you know day-night. That's actually what we need. So we will first look at what is typically available on websites to see what we can do with that. And then next week, we will go into the hourly data. So I give you some sources where you can find hourly data for locations all over the world to then compare both, to see what you can first learn from monthly data and then see what more information you get if you have a more detailed look at it. So that's the first thing we're going to do today, looking at climate data that are readily available on typical websites of your context, represent these graphically to start comparing between the different climates you're building in. So what I will show you still today is how you can download, where you can find it, how you can download it, and then I've put some Excel files on Toledo as well, where you can input it, and then it will graphically present your situation so that we can easily compare between the different contexts. Next module, we will look at hourly data. So what I would like you to do is the first step for analyzing your climatic data is making this kind of graph. It's giving a picture in a very rough way of a climatic zone to first start to understand each other's situation. So that's the first thing we're going to do. This is automatically generated once you have found the data and input it in the Excel file. So I will show you how you can do it. The Excel files, you can find them on Toledo in the module of today. And what we represent is sunshine hours, radiation, temperature, and humidity, and then rain. In the bars here, it's the rainfall. So that's what we're going to try, because typically that is available on every site of location you typically can find it. So let me explain first the first part, sunshine hours per day. There are two things, you see two bars for each month. So each column is 1 month, so we go from January to December. What you see in the first one here is a darker color. It's a higher number than the bluish color, which is a lower number. Well, what we do is first, these are the maximum values, meaning if it would always be blue sky there, no clouds, that would be the maximum amount of sun that you would get there. And how do we calculate it? Based on your latitude. So once you put in a latitude, we know the location on the Earth, and then we can calculate your position against the sun and know exactly what the maximum number of sunshine hours is on that location based on the assumption that there are no clouds. So that is automatically calculated in the Excel files once the latitude is input. And then you need to find the data on the real sunshine hours. It's the upper part. Once we have that, we can compare the two and understand what's happening there. Because if you have the maximum amount and the real amount and there is a big difference, then we know that there is in a position where there can be a lot of sun, but typically there are a lot of clouds. When there is a small difference, then typically there are no clouds or very rarely clouds. So then we see that it's very often a not humid situation because there are no clouds, so there is no precipitation. The second one is a radiation. It's actually giving the same thing, but it's not always available. So again, we can calculate the maximum amount, the blue line, based on the latitude, and that corresponds with the sunshine hours. And then you have the real data in pink, is what you should search for, but typically not always available. And then we have the upper as a backup, let's say, to understand the difference. Then we have, so the real and the estimated. The real is calculated automatically. The estimated is something you need to input in the Excel file. And then we have the temperature. We have different lines on the graph. We will first look in black to the mean, the monthly mean temperature. We will look at the mean minimum and mean maximum, so typically night and day, at 2 o'clock in the afternoon at the hottest, and during the night, the coldest temperature, to see if there's a big swing between day and night. And then you have the extremes, so typically it's also input there. On the website you find the extreme minimum and maximum measured over the last 30 years to show more or less, so this is the mean minimum, this is the mean maximum, to see if there's large swings over the months of over the years, let's say. And then we have the final one, first relative humidity and then also the rainfall. So the relative humidity are these. We again look at the average in black, the minimum, which is in the daytime, because it's a relative humidity. And then the upper one, the red one, is the maximum humidity when the temperature is low, so typically during night. And then the rainfall, we again have 3 numbers that you can input. The minimum, so you can hardly see it here. The average, so the mean, and then the maximum per month. which are typically data that you can find. Okay, so this is the input file. I've done it here for Brussels, but so you can fill it in for your own context. Yeah, there's a question, sorry. Yeah. It's the real. So the estimated one is the one, so the real one, sorry, the real one is the one you need to find. The estimated one is the one, the top one is the one that the file automatically calculates. I think I said it indeed in the opposite way. But so the real one is the one you need to find on the websites. The estimated one is in the Excel file then. It's the same as here. So if there are no clouds, we estimate based on your latitude what the solar radiation is on that location, but we don't have any information on the clouds because based on your input, we just know the latitude. So as here, the maximum number of sunshine hours is calculated, here the maximum amount of sun radiation is calculated, assuming there are no clouds. So typically, your real values should be lower. So here you see a small difference. That can be that your weather station has not the exact same latitude as your location. So that's why sometimes there is very small deviation that it's still higher than the maximum calculated. But that has to do with the latitude, which is not exactly the same. So the input is what you need to do. I will show you directly how to do it, and this is what will come automatically out of the Excel file. So you don't need to draft anything yourself. It will automatically be generated. So you see here different colors. The gray ones, it's just you can't fill in anything. The white ones are the cells where you need to input something. The yellow ones are automatically calculated. So don't touch the yellow ones, just fill in the white ones. And the yellows are calculated only once the white ones have been input, because they need these data to be calculated. So they cannot calculate automatically. So for example, the latitude, if you don't fill in the latitude, then the yellow ones will not be calculated because that's required to do so. But let's see what we need to do. So first of all, you give a name to your weather station. So it's for your specific case study. So first of all, you select a case study. And then you select a weather station that well represents the location of your case study. If it's the same location, the better. But you will not always find data of a weather station nearby or really at your spot. And then you need to check what's the best available for your specific case study. Can be the closest, but sometimes that's not the best choice because of a mountain or because of the sea or whatever. There could be a context that it's not exactly the best representative. So carefully check which weather station is best representing the location where you're building. So that's the first step to be taken. Once you know that, fill in the data of your location or your weather station. Should be nearly the same, but if it's not the same, the best is to fill in here the data of your weather station, but just mention in your text then if it's different from your real location. So what the difference is between the measured, the source of the data for the weather and your building location. There might be a difference, then explain that in your text later on, and not now, but in your presentation when we present, or in the paper when you're writing the paper. And then the first thing, based on this latitude, maybe first, I think I mentioned it here, the latitude depends if you're the northern latitude or the southern latitude. So for northern latitudes, you use a positive number. For southern latitude, you have to use a negative number and to enable the Excel to calculate the other parameters in a good way. So that's important. Be careful also if you open Excel, depending on the settings in your computer, commas or dots can be different for the decimal separator. So check when you fill it in that everything is logic. Sometimes it's a dot or a comma. You have to be careful that it's done in the right way. All right, then we have, based on this latitude, the first thing that is calculated is the maximum number of sunshine hours. So just based on the position. No clouds are there and assumed, and we calculate it automatically. And the same for the estimated maximum radiation. Yes? I would do it for the weather station, because otherwise it will be hard to compare the real values with the estimated ones, but just discuss in your presentation or in your paper what the difference is, so that you use that location to represent your case, which is located in another latitude, for example. Just explain what you did, but here in the Excel file, input the weather station data. Otherwise, it's a bit hard to compare with the estimates made. So these are automatically calculated based on the latitude, positive for northern hemisphere and negative for the southern one. Then you need to find the data on, if I go back, you need to find the data on the sunshine hours yourself and fill it in the white cells here just on top. And these typically will be lower because of the real clouds. So typically they should be lower. The same, if you have data on the radiation, you can fill it in here. And again, these should be lower than the maximum calculated in the Excel file, because typically there are some clouds present. The smaller the difference is, it means the more blue sky you have, so the less clouds you have. Then we have the temperature. What you need to search for is the mean minimum and the mean maximum. So the mean minimum is typically at night. The mean maximum is typically during the daytime, and the program automatically calculates the average of both, which is the mean day temperature then, so the average between minimum and maximum. Secondly, you need to find extreme, so that's automatically calculated, it's just the average of the other two. And then, then you have the extreme temperatures. That's typically for the last 30 years or for the last 10 years or whatever. The lowest measured in a certain month, and and the maximum measured in a certain month. It gives you an idea of the range that you can expect. Then you have the precipitation. What you need to fill in is the average rainfall in millimeters per month, and then the maximum in millimeters and the minimum in millimeters. That's typically also measured. It's easy to measure, so it's typically often available. And then the humidity, the mean minimum, the mean maximum, and typically either you calculate it as in the same way. So typically it's also available, the average, or you just calculate the same as I did for the temperatures. You add these up and you divide by 2 to have the average. And then this is the kind of outputs we are trying to get from you, but then in the colored one. But this is typically what you can find in many books on certain climatic contexts. That inspired us to make this form for you to prepare it. But so it shows you, it immediately gives you, when you put them next to each other, you can see the differences quite easily. So that's why this format is used. So this is typically done for many different climatic contexts, showing the different months, and then you have the sunshine hours, the radiation. Here it's only one number, so the real, not the estimated one. You have the temperature range, minimum and maximum per day, to show the swings. So here you see less swings, for example, than you see here between day and night, but also over the year it's much more stable than there. And then the humidity, we see low humidity or high humidity, and also differentiation. You see humid climates, for example, and dry climates. So that's how this kind of graphic representation can easily show you and position yourself against the others. So we will use it in the paper, but also in the presentations. So once you have sent the presentations, we can start comparing. So that's why we have the presentations in the sessions as well. All right, where do you find the data? Here you see some sources. So the Weatherbase or weather.com, World Climate, and so on. But you can also find specific weather stations for your country, typically in your specific languages. But these are also fine. And these are just websites to help you. But please have a look at your own country data where you can find anything. Sometimes the data are in different units than we want to have in the Excel file. Then you can use converters. So there are converters to go from one unit to the other. So here's a link to find it. So what we do is degrees Celsius for temperature. These are other international systems, but you will see it in the Excel file. If it's megajoule or kilowatt hours, for example, that you can see in the Excel file. So check carefully if the units are the same, of your source and what we expect in the Excel file. If not, convert them first before you input them in the Excel file. All right, that's the first assignment, to try to find the data for your location, input them in the Excel file. You don't need to submit it now, just keep it for yourself, and we will integrate it in the presentation in 2 weeks then, where you can present it together with the case study and the thermal comfort analysis. But you can already do it so that you have it already available. It's not a lot of work, but it's done. And then you can already go to, because next week we have another assignment, also a small one, but so it's split up in different steps. All right, that's about the climate. Before we go to the comfort, maybe have a break of 10 minutes and then we go to the next step.
Like
All right.
the building could be like an under construction stage,
Yes, that's okay.
and do we need the sections as well?
You need
Or
the heights, yes.
the basic heights, or maybe the heights of windows opening, all
Also,
that?
you need it, so, yeah.
Okay. And for the data which we define, like climatic and everything, that data will be putting on the normal Excel file, or
Yes.
is there a software where?
No, the Excel files. So the Excel file is in Toledo,
Oh,
and
oh,
there you need to put it in.
okay,
Yeah, so
okay,
there is an Excel file. Eh?
okay.
go to course documents, and then to the climate and comfort. And here, file. Monthly data.
Climate and comforts.
It's a module of today, yeah. Module 2. And you can find thermal comfort we'll also look at. So if you open it, so I can open the file. So you put in the white cells, the results are automatically generated.
Oh, how do you, okay.
So you just need to fill in the white cells. This is for Brussels, but you delete it and you replace it by your own data.
So the formula is already in the Excel. Okay.
Everything is there. Okay. All right?
Thank you.
All right, we will continue. So I just showed that the Excel files are on Toledo. So if you go to the second module of today, you will see there's an Excel file on representing monthly climate data. If you download it, you will get this file. Where is it? This file. There are two tabs, one with the input data, which I've showed today, where you need to fill in all the white cells. And then the second tab, it gives you the results. All right. Okay, then we go to thermal comforts. There are two important researchers that I want to refer to for the thermal comfort analysis. The first one is Fanger. Anybody heard of Fanger before? No? So he's well known because he studied for a long time how we feel comfortable. So thermal comfort was really his topic when he was a young researcher. And so he looked at thermal comfort of human beings by looking at human beings as a machine. So he wanted to know how much energy we take and how we release the energy. That's how he approached the human beings. So what comes in are drinks and foods, but also oxygen. That's the three sources of energy we get or of inputs we get. And what we do with it typically is we have physical labor or mental labor. So we need energy for that. So that's the direct energy we use for it. But typically with these activities, we also release heat. So when you run, you need energy to move, to be able to put your feet in front, so to let your muscles work. But at the same time, you will release heat because your temperature in your body is raising by these activities. So the more intense the activity is, the higher the temperature of your body, and so you will need to release the heat as well. So it means that we produce heat even when you just sit down. Your body consumes energy to keep your temperature stable at 37 degrees more or less. If you would not produce this heat, you would not survive. So that's why your body, even if you're just sleeping, you are consuming energy. You need this energy so you need to eat even if you wouldn't do any activity at all. But the more heavy the activity is, the more heat you produce, of course. So when you go running, you produce much more energy than when you are sleeping, and more heat. So what his hypothesis is to feel comfortable is it depends on how you can release this heat. If you cannot release it, then you will feel too hot sometimes, or when you don't have enough energy for the activities you're doing, you will feel uncomfortable as well. So thermal comfort is mainly based on the temperature of the skin, if you can release it or not, and on sweating or not, if you're able to produce moisture, if you can sweat, yes or no. So only when these are in a situation where it's balanced with the heat you want to release, then people feel comfortable. So when you, for example, are in an area where it's very humid, and so you cannot sweat anymore because the area is already full of water, then it's much more difficult to feel comfortable than when you would have the same temperature but you're in a dry environment. So the humidity has to do also with this ability to sweat. So this comes a bit back to what we said before, the different ways of exchanging heat through radiation, conduction, convection. And so it depends on our situation. It means that, first of all, the level of clothing will determine if, in a certain situation, how comfortable we feel. That's the insulation level of the clo value, we call it. It's the value, the insulation level of our clothing. The activity will be important. If you have, in a certain situation, so typically, for example, the temperature in a bedroom is lower than the temperature in a living room. Why? Because we have an additional blanket on top of us, meaning that our insulation level is higher than when you are in a living area where you don't have these heavy blankets on top of you. The higher your activity level is, the more heat you release. So typically the temperature in sports facilities is lower than in an office space where you just sit down. And so there the temperature should be higher to feel comfortable than, for example, in a sports facility where you are playing basketball. There the temperature will typically be lower to be sure that you can release the heat. So it means that if you look at persons, their feeling of thermal comfort depends on the humidity, but also on the air speed. It has to do with convection, air temperature, the radiant temperature. So you have, I will explain in a second, the metabolic rate. So how high your activity is, how intense the activity is, that's the metabolic rate. And then the clothing or the insulation. So if you have thick clothing, if you have a blanket on top, yes or no, that will determine how comfortable you feel in a certain situation. What's the difference between air temperature and radiant temperature? Well, typically every object surrounding us has a certain temperature. If the air temperature is 20 degrees inside of 21, but you are sitting next to a cold window because outside it's cold, you will feel less comfortable when you sit next to a radiator with the same air temperature. So your comfort feeling is also influenced by the objects and the temperature of the objects surrounding you, because you exchange heat with them. And if you have cold objects, you will radiate to them, meaning that you will feel less comfortable than when you are close to warm objects with the same air temperature. So that's the radiant temperature. So what Vanger did is try to put all these inputs, energy we get from food, from drinks, and the exchange of heat, the heat we release, into a formula. Because he says you are only in balance, so the heat loads means is the difference between the heat production and the heat losses. So the more heat you produce, the more heat should be lost. You should release more heat to have a neutral heat load, to feel comfortable. If you produce more heat than you can release, you feel too hot. When you produce less heat than you lose, you will feel cold. So that's the comfort feeling related to the heat load. And this heat loss had to do with conduction, radiation, breathing, evaporation, while the heat production has to do with what you are doing. So the activity. You produce more heat when you run than when you're sitting down, for example. So you feel too cold when it's lower than 0, the heat load. You feel comfortable when it's 0, when you're in balance, let's say, and you feel too warm when you produce more than you can release. That's the simple formula. To show you the concept, he really translated that into all the mechanisms behind. I will not go into detail here. The only thing what I want to do is highlight that we have some parameters that we can influence these heat losses or not, or the heat production. And that depends on the parameters in the formula. So without explaining everything in detail, we see some parameters appearing. So it's the clothing, so how the warmer your clothes, so the heavier they are, the more insulating they are, the less the heat release is. So that's a way of protecting ourselves against cold climates. But also if you cover your full body or not, has to do with this clothing insulation. And then the surface temperature of your clothes. So if you have a cotton T-shirt with a low temperature, or you take it from the air tumbler, so to give it a higher temperature, and you put it on, you feel completely different in comfort. So also the temperature of the clothing has an influence. So the activity is important, so what you're doing. So the same situation where you have a high activity and a high heat production, you will feel different in comfort than when you're just sitting or lying down. And that has to do with also the free energy production. So if you are running and a lot of the energy goes to the muscles, then a lot of energy has nothing to do with heat. So the heat is something else than the energy needed for your activity itself. So both are related to each other. But typically the higher your activity, the higher the heat production is. So these are typically linked to each other. And then you have a lot of outdoor variables like the air temperature, so external variables. The air temperature, the mean radiant temperature, the speed of the air, so it's for the convection of the heat, and then the how moisture the air is, so what's the vapor pressure is around you. That determines the comfort. So it will mean that when we look at comfort, we have to take all these parameters into account. So when you analyze a room or a building, the thermal comfort will depend not only on all these characteristics, but also what you are doing inside, what you expect that people will wear inside, if they will, which kind of activity they will do inside, will determine what kind of variables we are striving for. So the temperature could be lower when there is a high activity, or the wind speed could be higher than. So it really depends on what you're trying to achieve inside. Now, this is an important formula to calculate the heat balance, but it's hard to interpret if people feel comfortable, yes or no. So that's why he translated it also in a feeling, how people feel. So this heat load, which he first calculates, if it's 0, minus or plus, he has translated that into by surveying people to understand with a certain heat load if they will feel comfortable, yes or no. And that he calls the predicted mean vote. So the predicted mean vote, sorry, I lost my mouse. The predicted mean vote, which you see here, is how, I don't see my pointer anymore. So let me do it like this. So the predicted mean vote is how people predict they will feel. So if they say 0, they give a number of 0 when they feel neutral, not too hot, not too cold. They have to give a number of -3, or the calculation. I go back. It's not about service now. It's the next slide. So here, once he has calculated the formula, he needs to understand how severe the uncomfort is, because you can have a negative or a positive value, but you don't know what it means. So that's why he gave it a scale. 0 is neutral, but -3 means you're really feeling very cold. Then your heat release is much too high compared to the heat production. If it's +3, the scale +3, it's meaning you really feel too hot. So that's the predicted mean vote if people feel either comfortable or not, and it depends on the metabolic rate, of course, so calculated in the previous slide. This formula, how he, it's really annoying, how he feels, so how this number is related to the metabolic rate calculated in the previous one. So all the parameters that I described in the previous slide are linked to the -3 to +3 scale through this formula. And this formula he determined based on surveys to find a link between how people feel, how many people feel comfortable or not, compared to these metabolic rate results. And that's done based on the percentage of people who feel dissatisfied. So either too hot or either too cold. So there is a link between this predicted mean vote, feeling neutral, cold or too hot, and the percentage of people that do feel that. And what's the link? Well, actually people, if 10% of the people feel comfortable, he says, okay, it's okay. While if it's more than 10%, either you are in this zone, in that zone, or in that zone. So here it's really, most of the people feel uncomfortable, while here it depends. So for example, 20% of the people feel uncomfortable, and here 10%. So this was for him the range. If you are within the 10% of the people, if 90% of the people feel comfortable, he gave it a label of comfortable. just to understand how people feel and what the real numbers are of this exchange between heat production and heat release. And the uncomfortable feeling can be either too cold or either too hot. And that's the link then he made through these surveys between what people feel and then the predicted mean vote, which is show a value between -3 and +3 and has this curve related to the percentage of people who feel dissatisfied. This is typically used, so if less than 10% feel dissatisfied, he calls it, so it's the PMV between -0.5 and +0.5. This is for him a comfortable situation. So the absolute value of the predicted mean vote should be below 0.5. These values can be calculated in building simulations. So there are software packages that calculate the energy demand in a building based on the characteristics, but can also assess the comfort. And so the comfort will be different in any location of a building because there is a window next door or because there is no access to direct radiation whatsoever. So for each building, when you know all the parameters behind, so if you know the temperature, the climatic conditions, you know the window characteristics and so on, you can assess what the percentage of people are that are dissatisfied. So this curve there, and then you can make the link to the predicted mean vote as well. So here you can see, for example, that here in that place, many people will feel, more than 20% will feel uncomfortable because it's probably too hot. While in others, they feel really okay, or they feel a little bit discomfort, or there's a higher chance that people feel uncomfortable, yes or no. And then you can change your plan and recalculate it again to see how it changes the feeling of comfort. Now, the 10% that he defined is a little bit different interpreted by ASHRAE, which is an American standard for heating and air conditioning of buildings. Well, you see that they keep the 20% of dissatisfaction as a level of comfort. So it's less severe, let's say, than the first predictions of Fanger. Now, to do this kind of analysis, you really need a lot of calculations, and you need software packages that allow to do that. You need detailed information of your building, which goes beyond what we can do within this course, because we have limited time. So therefore, we will use another mean to assess our comfort, and it's the thermal comfort assessment of Olgay, Victor Olgay. What he did it based on a lot of case studies as well, and a lot of surveys. He tried to identify what influences comfort and what is the comfort zone in a more less mathematical way, let's say, but a more based on a lot of measurements and surveys. And what he did then is translate that into a chart. So what he did is he defined the comfort zone, let's say, where people feel comfortable. And what defines the comfort? Well, on the one hand, the temperature, that's on the vertical axis. And then on the horizontal axis, the relative humidity. These are the two main parameters defining the comfort zone. He did that, first of all, so this is the green zone. If you're in that zone, every combination of temperature and humidity in that zone means you feel comfortable. If you're outside that zone, you don't feel comfortable. But if you remember, there were many different parameters defining the comfort feeling, so there are some assumptions behind. He assumes this is the comfort zone for people sitting down, white-skinned people, without direct solar radiation, so in the shade, let's say, and with summer clothing on. In that situation, this is the comfort zone. So this is divided or defined by temperatures, minimum and maximum temperature, by a minimum and maximum relative humidity, and the top corner is not comfortable when you have high temperatures combined with high humidity, because the release is blocked either by sweating or by even radiation or conduction. It's just not possible anymore with these two any of the way. So that's why that zone is uncomfortable. But it means that the comfort zone is only in that situation, these temperatures and these humidities. It can go up. So it means at higher temperatures you can still feel comfortable when there's a lot of ventilation. So when the wind speed goes up, your comfort zone goes up. Then you still feel comfortable, or you only feel comfortable when it's a bit warmer. And so he links the wind speed, how much wind speed you need for each temperature rise, let's say. On the other hand, you can still feel comfortable with lower temperatures as long as you have sufficient radiation. So if you go sitting in the sun, you can still feel comfortable with 18 degrees, for example, because you get the energy from the sun at the same time. So the lower you go with your solar radiation, with your comfort zone, you still feel comfortable when you get sufficient direct radiation. So that's the sun. So the more sun, direct sun you get, the lower the temperature should be to still feel comfortable. And then this original comfort zone sitting in the shade is not comfortable anymore, even when there's also direct sunlight or sun radiation, because then you are too hot. So these are linked. So his comfort zone, his basic comfort zone, is under the assumption that you're sitting down, you have light clothing, you're a white-skinned person, you are sitting in the shadow, and then that means that this range is the comfort zone, keeping in mind that it shifts up when there is more wind, more ventilation, and it goes down when you have direct solar radiation. Or when you have other types of clothing, if you are running, for example, it goes down and so on. So keep this in mind when interpreting these kind of figures. And that's the second part of the assignment today, is to assess with the weather data that you had collected and that you filled in. You also put the same data in this second Excel file on Toledo, and it will assess where you are compared to this comfort zone. So what we did is for you prepared the comfort zone. So what we see, you have an Excel file where this graph is input without these lines. These lines are for a certain situation. So it's Belgium, I think. No, it's another country. What the yearly temperature and humidity is compared to the comfort zone. So this is already the data which are input here. Yeah, it's Brussels. So these data are shown here, but you get an empty chart with in green the comfort zone as defined by Olgay. And then you see here the additional lines. If there's a lot of wind or wind speed and you can use it in your building, you go up the comfort zone. Or if you have access to solar radiation through the design, then it goes down a bit. And that helps you to understand how your comfort is in your specific situation. So what we do, we have the temperature, we need the temperature and we need the relative humidity, mean, maximum, and minimum for both, to analyze in the first step how your location is regarding this comfort zone. Is it too hot? Is it too cold? Is it okay? Is it too humid? Is it too dry? Just to give a first idea. So it is basic information that you also had to gather before for the weather analysis. We will check how comfortable you are. We will use this chart of Victor Olgay. There is another one, the one of ASHRAE. Did anybody of you already use this one? Yes. So it's actually doing the same thing, but we had to make a choice not to make two different charts and make it even more confusing for you all to understand each other's situation. We decided to go for Victor Olgay, but it's actually more or less the same thing. So what you here see is the axes are different. So what ASHRAE did is it's the same climatic zone, thermal zone, sorry, but now the temperature is on the horizontal axis and it's the absolute humidity which is on the vertical axis. You still see the relative humidity by lines. And then you have a comfort zone again, which can go up if you ventilate a lot or go down when you have radiation. So it's the same thing, but it's a different representation. But to not make it more difficult to interpret everything, we will all stick to the same one of Victor Olgay. There is a little bit more information in this graph because from the graph you can also understand some other things, like so you can read the absolute moisture content, which we cannot do from the other one. The dew point temperature, so when we have this change from, so when you are 100% relative humidity, it's the dew point at that temperature. When you absolute humidity equals the maximum amount, we call it the dew point temperature. So at that temperature, your absolute amount equals the maximum. And so you go from vapor to water. This is also readable from this graph. So there are a bit more information there, but I will not go further into detail. I think the ASHRAE, the Victor Olge is sufficient to get the first idea. Because then you go even, so you see it's more, so there's a lot more information on these types of graphs, but I will not go into detail. But the principle is actually the same. You have the comfort zone, and you can then, from these graphs, for example, if you're at a certain point, see what you can do to get in the comfort zone. So you can either dehumidify, so then your absolute amount of moisture goes down, and then you can combine it with cooling to get there, or you can first try to cool and then see how you can, on the other hand, reduce relative humidity to then heat up again to get in the comfort zone. So there are different ways to get into the comfort zone, but that we will not do. What we will do is simply plot our data on the Victor Olge's chart, knowing that it's more or less the same information as on the ASHRAE chart. We will learn from our average monthly data where we are situated compared to this chart, and then next lessons we will look at more detailed data to have a more in-depth interpretation. But so this is just to get a first idea of the thermal comfort situation. Just to show you, the same data can be plotted on ASHRAE. It's also in the Excel file, so if you want to have a look at it, you can have it, or for later or whatever, you can use it. But now for this course, we will all look at these, but you see it's just turned. So this is now temperature and absolute humidity, and you see we are on top of the comfort zone, but here we are next to it, so it's actually the same thing. Yeah. So what you see, you have one line for each month. So for January, February, March, April, May, you have one line. Each line consists of 3 dots, the minimum and the maximum, and then the average in between. And that comes automatically. That comes automatically from the Excel file. So you have the minimum. But here you can see what I said before, that the minimum temperature comes together, so the highest temperature here comes together with the lowest relative humidity. And the lowest temperature comes together with the highest relative humidity. So all the direction of the lines should be like that. If you have another direction, something went wrong in your input. So because we assume that the absolute humidity does not change too much per month, it means that with the highest temperature, you can hold the highest amount of moisture. So it means that your relative humidity is the lowest. So this is actually here, the minimum is a point at night. And then at the daytime, the highest temperature is at daytime and comes together with your lowest relative humidity, while a point at nighttime, the minimum temperature comes together with the lowest temperature and the highest relative humidity. The absolute humidity is more or less the same, but so the relative humidity drops when the temperature raises. Okay. So this is what we're going to do. If I go back here, if you remember the input from the weather data for the first part of today, we had different data. Sorry, I need to go back fully. So we said we're going to search for data on temperature, minimum, maximum per month, and the average is calculated. These values are then used for the temperature per month also in the thermal comfort analysis. And then this is combined with the data on humidity. So the relative humidity mean maximum and mean minimum are also used. So you have 3 dots per month, the combination of this temperature and humidity. So you don't need to search for additional data. It's the same data that you input in the two Excel files. First in the weather analysis and then in a thermal comfort analysis. And the graphs are then automatically created again. So you don't need to make any graphs. These are automatically calculated. So with that, I would like to end with the assignment. So you make your choice of your case. You look for a weather station that is well representing your case. You look for the data for the weather analysis, the climate analysis, and then for the thermal comfort analysis based on monthly data. So it means for the case, let me repeat it, it should be a housing unit, so a residential building. Typically in the country you're used to live in. It should not be your hometown, but at least the country that you understand, so that you can interpret the data you gather in a good way, that you understand if it's correct, no, yes or no. Can be an own project, or it can be a recent case that has been built or is being built, or it can be a traditional vernacular case. So either you have a good case as an example case that you just want to learn from, or it's a case that you doubt it's functioning well and you want to check if you could improve it, for example, from a thermal perspective, mainly solar access, thermal comfort, and then the cost assessment in the second phase. I also posted the examples of last year that I shown in the previous lesson on Toledo, so you can also always have a look to inspire you. Then you look for that location for weather data. You give it in the Excel file that I've shown. The white cells need to be filled in. The yellow ones are automatically calculated. Here again, you find some sources and then give your Excel file the following name. Your latitude, 2 numbers. So not behind the comma is not needed, 2 numbers. You call it climate, and then the country code, the city, and your name. For me, I will need to put everything together at the end to make to guide you in the presenting session, and it makes me much easier that I can sort it according to the latitude and take out some good examples and to cover everything. So that's why it's so structured. The latitude is just 2 numbers, and then the digit of your country code, you can find it typically on Wikipedia, for example, so it should also be 3 letters. For now, you don't need to hand it in yet. I will put it on Toledo and the discussion forum where you can then upload everything. There is no deadline yet. You will need to present it in 2 weeks' time, so by then it should be ready, but not by next week, so you have time to do this. So these are some examples of weather data for Belgium, for example, where you see the average temperature on a monthly basis, the minimum and the maximum temperature, and then the highest recorded, these are the extreme temperatures, to give you an idea of what you're looking for. And then you also have the precipitation, for example, the wet days, but that we don't need, average sunshine hours, that is what we need. And radiation is not included here, so I don't have information on the radiation. And then I just keep it out. I delete the values that are in the Excel file then, because otherwise you mix Brussels data with your own data, of course. So delete what you don't have. And this will be the outcome, so that you will have then for the presentation and for the paper. And then second, you download the Excel file for the thermal comfort analysis, which is also on Toledo on this module of today. And you copy-paste the values for temperature and humidity in that file. You save it again on the same name, but instead of climate, I think it was, now it's Olgay, just that I immediately see what it is. And then this is the kind of outcome you will get. First, you will get for each month the average temperature and humidity. So without the lines, just the average, to see how it evolves over the year. And this is the yearly average that's automatically calculated as well. And then in a second graph, you will see the spread over the day, to see the difference between day and night. So then you have the 3 dots per month. So once you have 1 dot per month, which is the mean temperature and mean humidity. And then you have per dot a line, which is representing also the maximum temperature and minimum humidity compared with the minimum temperature and the maximum relative humidity. So that's the 3 dots per month. All right? That's about it for today. Not sure if you have any questions on this part. Everything clear? Perfect. All right, if you by next sessions are trying, it's good to already try to find the data. If you have any questions, let me know, then I can see if I can help you finding it. All right, okay, thank you very much. So maybe for those, because some of the students here are following also the Master in Conservation and cannot be present every week, so I'm making the recordings, so you can always look at it if you would like it. Only for the presentation sessions. If you cannot make it, please let me know, because I will prepare it and select some people to present, but then I should know if you will be there, yes or no. All right? Okay, thank you.